Hello, everybody. Welcome to my presentation. Today's topic that I will be presenting is called Detecting and Identifying Faulty IoT Devices in Smart Homes with Context Extraction. My name is Vedran Simunovic, a graduate student at Georgia Tech. Let's get started. First, I'd like to acknowledge the authors of this paper. I hope I can do justice to their names. If they're listening and I pronounce it incorrectly, I'm sorry. The authors are Jiwon Choi, Hayoung Jung, Jihoon Kim, Youngyu Ko, Wonup Young, Hanyun Kim, and Young Kim. And all of the researchers who actually wrote this paper are from the Pohang University of Science and Technology in Pohang, South Korea. This paper was presented at the 2018 48th Annual IEEE IFIP International Conference on Dependable Systems and Networks in Luxembourg City, Luxembourg, between the 25th and 28th of June in 2018. The research was sponsored by Samsung Research Funding Center of Samsung Electronics under project number SRFCT B1403-04. Let's get started with the topic. So first, some background information. I'm sure many people have seen what a smart home is, and in this paper, we won't be exploring all aspects of a smart home. So for example, this smart home has very many sensors and actuators and other things. You can see here, there's a smart TV and a video door, phone system, body sensors, cameras, etc. What this paper will be focusing on is environment monitoring, a little bit of energy management, and home automation. So things like remote service platforms with eHealth and monitoring heart rate and other biomedical parameters and such things will not be explored. To get a very high-level overview of where the presentation is going to go, I just wanted to give an executive summary first so people can have some idea of about what the topic is and kind of where it's going. So just an overview. Basically, smart homes have poor self-diagnostic solutions currently. So that's what this paper is going to try to change. Essentially, a smart home with very many sensors, as you can see here, there can be a lot. They have very poor algorithms for detecting if one of the sensors now does not work. Basically, what this paper will do is it will show a method, in principle, an algorithm for accurately and quickly finding faulty IoT devices in smart homes. So if somebody has 100 IoT devices in their smart home, they don't want to look for that one that's broken. They want to be told, okay, that one is broken, go fix that. So the solution here is going to be through context extraction, be through an algorithm that the researchers call DICE. And the end result is that it's a very highly accurate solution with very high potential for industrial application. So what that means is maybe in the next 10 years, systems similar to DICE or even better systems will be deployed with smart homes because the necessity is essentially there. Currently, smart homes exist. They say, okay, here are all these sensors that you can buy, put them inside of your home, set them up, but when something goes wrong in a year or two, and one of the sensors fails, well, then that's your problem, essentially. Okay, so we've gone through the acknowledgments, the background, and the executive summary. What I want to focus on now is going into the introduction to the actual research. We're going to look at the related work, and then the actual DICE, which is the detection and identification with context extraction algorithm. After that, the experimental setup will be explored, as well as the evaluation of the results found in the experiment or the experiments, and after that, the conclusion. So IoT devices fail frequently due to harsh environments. Being notified of the failures is an area that can be improved upon very much. current solutions are impractical for commercial use. We're going to go into that a little bit later because they require just a massive amount of user interaction, and the users, I don't think anybody wants to go and dive into self-diagnostic problems after setting up a smart home, which most likely takes an enormous amount of time anyway. So DICE is essentially an automatic faulty device detection and identification solution based on context extraction. So the algorithm consists of two main phases. There's a pre-computation phase where essentially the algorithm is not actually monitoring and detecting if an IoT device in a smart home is failing or not. That's just where the algorithm's parameters are being set up essentially. So what the algorithm needs to do is set up a sort of ground truth as to, okay, what we can currently see in the smart home is a valid state. And then the real-time phase is where, when all of this data that's being produced by all of the IoT sensors in the smart home is actually collected, it needs to be analyzed, and that's what happens in the real-time phase. As essentially all of the data is being continuously analyzed, the results are being essentially output to the user. The acceptance criteria for something like this, they're essentially defined by the researchers as usability, generality, feasibility, and promptness. So essentially, usability goes into whether the system is user-friendly. Generality is going to go into if this supports a very general smart home that has, for example, sensors, actuators, numerical sensors, binary sensors. So essentially not just your light detector, which tell you if there's light outside or not, but also some kind of numeric sensor that can tell you, okay, there's this much light, or okay, now there's even more light than there was 1 hour ago, things like that. Feasibility is going to be, how likely is it that a certain system will be deployed? Some of the systems that will be shown, they take a massive amount of time to actually detect the fault, on the order of 12 hours. So that's not very practical. And that's what this algorithm is going to show, and it's going to improve upon that by orders of magnitude. We're going to see that's going to be about a half an hour in the worst case. Promptness goes into that same criteria. How fast does a user get notified of a fault when it happens? So this topic actually has a lot of research already being done actively. The methods for identifying faulty IoT sensors, they're mostly focused around network level approaches, homogeneous approaches, and heterogeneous approaches. So what a network level approach would be is, let's say a smart home has 10 devices, everything's communicating over Wi-Fi, and when packets stop being received from a certain sensor because the connection is lost, then immediately the smart home monitor will know, okay, well, I haven't received a ping from this sensor in a while, it must be broken. So this is a very basic approach, but it works somewhat. The current approach, DICE, is going to be a lot better. We have homogeneous approaches too. So say somebody wants to detect light in a smart home. So what they'll do is they'll set up redundant sensors. For example, they'll put 10 light sensors in the same area. So it'll be very easy to identify if one of them fails, because 9 sensors are saying there's light outside and there's one that's saying there's no light. And the heterogeneous approach, which has the biggest potential for industrial application, is where DICE is going to be. And heterogeneous approaches are basically, we have a smart home and we have 10 different sensors, and we're going to use them together to figure out if something is wrong. So an example would be, let's say a smart home has a light sensor, a humidity sensor, and a temperature sensor. and the location is, for example, in Arizona, and you can know that it's daytime or nighttime based on, let's say, that the temperature and the humidity. So the light sensor will say that it's day, and the temperature will say it's very hot, and the humidity it'll say it's very low. But then in the nighttime, it'll say that the temperature is still hot, which if you've been to the desert before, it actually gets very cold at nighttime. So then you could immediately know, okay, well, my temperature sensor isn't working correctly, because you know, okay, the light sensor is telling you that it's dark outside and it's been 12 hours since the last light reading, so you have to assume it's nighttime, and things of that nature. Like I mentioned, network level solutions find faults through network connectivity failures of the device. No data has been sent by the device in a while. Homogeneous approaches focus on clustering similar sensors together to find faulty outlier sensors among a set. Then heterogeneous approaches use the relationship of different types of sensors to each other to find a faulty sensor, essentially. The bulk of the related work and what DICE is being compared against is going to come from the heterogeneous approaches. The heterogeneous algorithms support complex smart home setups consisting of large numbers of different sensors. So the existing systems, or algorithms, I should say, that DICE is comparing itself against are called SMART, Failure Sensor, IDEA, Clean, and Sixth Sense. The performance of DICE, the heterogeneous algorithm, is compared with other heterogeneous algorithms based on the mentioned acceptance criteria. And as you can see, most of these existing systems, they just don't meet all of the criteria. And that's what makes DICE so great, is that it has a large potential for being used in industry because it meets all the necessary criteria. A typical smart home thus consists of a cloud server where the data will be sent to for it being analyzed or accessed by a dashboard or a smartphone or something like that. We have the device that actually sends or forwards the data to the server via the Ethernet connection, for example. This gateway essentially will collect the data from the aggregators. You can think of an aggregator as, for example, an Arduino board, and then the actual IoT devices would be, for example, your temperature sensor that's connected to the Arduino, then your light sensor, humidity sensor, and so on. An overview of DICE. So I mentioned that there's a pre-computation phase and a real-time phase. Essentially, the pre-computation phase consists of context extraction. So what's being done there is there is a correlation extraction phase and a transition extraction phase. I'll go into that a little bit later. In the real-time phase, there is detection, which basically will check if a fault exists, any kind of fault, and that'll be checked by the checks from the correlation. You can see first the correlation is extracted in the pre-computation phase, and then the current sensor readings are checked against that. That's where the correlation extraction comes in the general case. The transition extraction is what will be used if the correlation doesn't show up properly. So for example, a device isn't completely dead, but it's just producing the wrong data. Looking at the correlation, you would think it's plausible that it's still working, but based on the transition check, you can see, oh, well, the value has been the exact same for the past 24 hours, for example. And the final part in that would be the identification, which essentially means, okay, now we've detected that a fault exists. Let's find the actual faulty sensor, essentially. The context extraction is probably the most important part in the paper that lays down the foundation for the rest of the parts in the analysis. So essentially, the system extracts the correlation and the sensor state information collected from the IoT sensor and actuator data. The raw sensor readings, for example, at time 0, 1, and 2, are collected, and a sensor state is created. This sensor state is referred to as a sensor state group. It can also be thought of as a context, so we have a certain current context of the sensors. They form groups, so we can have like a context over a period of time. The next part deals with transition extraction. So we have basically now our groups, and over time we want to know what kind of transition happened. So we can have group to group, G to G, group to actuator, G to A, actuator to group transition probabilities. So what this does is it basically computes a probability matrix of one sensor going into a different state. And then based on that, the algorithm calculates if a transition did not occur, that would be a fault. Or if a transition did occur and it's as expected, then that would line up with what the algorithm would define as a normal operating sensor. There is one more theoretical possibility, A to A, but that's not considered because that data can essentially be inferred from the existing matrices. The detection part essentially takes a real-time current correlation and lines that up with the correlation that was created in the pre-computation phase. If the current correlation lines up with what is actually in a group, then further processing needs to be done on it. So we can't detect that there is a fault or that there is not a fault. We can just say, okay, it seems to be working normally. We still have to do some work on that. The current sensor data can also line up with probable groups. That's where the likelihood of a fault is increasing. The transition check is then the calculation that takes the most amount of time. So the correlation check is just a very fast, okay, is it in the ballpark or is it not? And the transition check is what then takes the most amount of time because there are a lot of computations to be done because there are a lot of matrices with a lot of values to be checked against. After that's done, the identification of the faulty sensor can be done next based on the previous data. So what will happen is, let's say there are 10 sensors and one is faulty, one of them will not align with the expected normal behavior. And based on that, that sensor will essentially be detected as not working properly. The experimental setup, so what the researchers did is they took some open source data that's marked here by House A, House B, House C, TWR, and HH 102. So most researchers that are in this area, they'll be they all have access to these openly available data sets, but that wasn't enough for this research because the openly available data wasn't too realistic. It seemed that they didn't actually perform the experiments and collect the data in an actual smart home or in a smart home that's very objective. So maybe the data collected there was just so that it can fit the current research being done by the other universities. That data was collected from the Intelligent Systems Lab in Amsterdam and from Washington State University. What the researchers did is, in addition to verifying their algorithm against the existing open source data that most researchers have access to, they also collected their own data, noted here with the prefix D underscore, using their own smart home. And the reason why the suffix is the same is that in a certain experiment, certain activities were done, and they just repeated those same activities in their own setup to be able to better compare the results. So the experiment spanned about 1 month with approximately 5 different volunteers inside of the smart home at various times, where the first 300 hours of data collected was used for the pre-computational phase. This is what kind of sticks out at me. When a smart home system would be purchased, I guess, I as a user wouldn't really expect to wait 10 days for any kind of, or 2 weeks almost, for any kind of self-diagnostics to kick in. That's usually when the guarantees for the sensors will expire, or where, you know, your receipt will only have a 2-week return period. And if this stuff just kicks in after that, well, then I can't really get my money back, essentially. What happened in the experiments is that the activities were performed by the volunteers, and the sensor data was simply collected with actual working sensors, so the sensors were working correctly. So the fault needed to be inserted artificially in post-processing, essentially. And then the researchers knew, okay, that's where I inserted my fault. Let's see if the algorithm will detect that. And now going into the evaluation of the results, we can see here that the detection accuracy, which basically means that some kind of fault occurred, is pretty high. The precision is high, as well as the recall. So the average precision is about 98.2%, and the recall rate is about 97.9% for the 10 data sets. And then the identification accuracy is a little bit lower at 94.9% for precision and 92.5% for recall. So that is essentially figuring out that that particular device is indeed faulty. There's some more analyses that were done. So comparing this system with existing systems take about 12 hours to detect that a fault occurred, or even to identify that a certain sensor is faulty. Keep in mind, the existing solutions don't have all of the functionalities that DICE does. The actual computations for example, the correlation and the transition, they don't take very long, as we can see down here. They're in the millisecond range. But for actually detecting that a fault occurred and identifying that faulty sensor, that takes a little bit more time. So as I've said, 12 hours is the average for existing systems. In the best case, DICE takes about 7 minutes to detect that a fault occurred on average over the 10 systems. In the worst case, it's about half an hour. And the identification time, that will always take longer than the detection time, because the identification time, it includes the detection time and then actually figuring out which sensor is actually not working. So looking at the actual computations again, correlation checking and transition checking and identification here. The correlation degree and the number of sensors of the data set. So this doesn't necessarily have to correlate with the number of sensors. So for example, there are a lot of sensors in HH102. Correlation is 3.8, but then not so many in DICE, and the correlation is a lot higher. So the correlation is basically, okay, going back to the example about Arizona, you know, if the temperature sensor, humidity, and light sensors correlate highly, then that number is going to be greater. And then the ratio of detected faults. So basically, if a fault is such that the device completely stops working, doesn't send any more data, that can be very easily identified in the correlation phase. And that takes very little amount of time. If, however, a device is stuck at some value, well then, to detect that fault, first the correlations need to be done, the correlation calculations, but then because no fault would be found there, the fault would only be found in the transition calculations, which take a long amount of time. And that's why that takes longer to find. So essentially, existing algorithms have not been applicable to the real world. Many times users would have to label the data collected manually to make the algorithms work, and that's really not user-friendly. DICE overcomes all existing deficiencies in current state-of-the-art, bringing this real-world solution. As I've said, DICE identifies faulty devices successfully with an average of 94.9% precision and 92.5% recall. DICE takes about 3 minutes to detect faults and an average of 28 minutes to identify faulty devices. That's the identification phase. Existing algorithms take an average of 12 hours for both of those, and DICE can contribute to building a highly reliable smart home. Okay, I thank you guys for listening. I hope you learned a lot, like I did, and thank you.